Assalamu alaikum. So today's second day on 13th summer school at LHC Physics, where students learn about mostly Large Hadron Collider. This is the large physics experiment in France and Switzerland near Geneva. So this is day 2 on 13th summer school, and for the day 1 I uploaded all the $1 million lectures on my YouTube as well as my Facebook page. If you missed, you can watch there. It's basically for the particle physics researchers to learn about the large physics experiment, Large Hadron Collider. So this is very interesting. Today, same, I'll upload the lectures on my YouTube as well as Facebook page. Stay tuned with me. Thanks.
So you are throwing away the low momentum, the low PT neon, and also you are throwing away those neons which are going outside the detector coverage. So the coverage is limited to plus minus 2.4. But with the newer one, we will go to plus minus 3. So this means the shaded region will be included. So we will not be missing the neons which are coming from the decay of the mixed particle, just because we are cutting theta equal to plus minus 2.4. So this means this will increase the coverage of the CMS detector in eta, and also the coverage of the CMS detector in PT, especially in the lower region. So this I already talked about. We will be gaining about 15% more significance if all the contacts are within 15 microns or 14 microns. So that means we were able to build all the lasers, all the contacts within 15 microns. So once we were able to do this, we send them to CERN and then to Stanford and Stanford. Then we started the production, and the production has been done in the company. It's a metrology setup in the production. You have to do it by the CMM, the coordinate measuring machine. So now it has been programmed and it can automatically measure the linearity of all the contact points. We have been able to make 3 pre-production ladders. These are again the linearity of those pre-production ladders. They are all now at CERN.
Quite some intricate details about each of these individual detector components and the reconstruction, the local reconstruction that goes into those that then comes together in this particle flow to then be used as input for then actually creating these sort of higher level objects at a later stage. And then the later part will then focus on these high level objects and then see how we progress also, and how useful it may be. That we may also try to have some sort of hands-on aspect also now. But yeah, let's let's start first with a brief intro on what jets are traditionally seen at, let's say, and the clustered by the different algorithms look like, and well, for us experimentalists, this NCP algorithm has been the main name of the game for sort of first finding jets that then we can also more or less straightforward and calibrate. So for that, it's sort of convenient if they are more or less regular shaped. And this NCP algorithm with this choice of the exponent and clustering hard particles first, the KT algorithm with cluster soft particles first, with many surfaces relatively irregular shape, and then the Hammad-Shaukat algorithm is this angular clustering, which is then actually very often used in combination with the NCP algorithm. So that first we find with the NCP algorithm jets, in particular these white jets, and then requirements for what makes a good jet algorithm, and in particular these two requirements of infrared and collinear safety. So that is the fact that the requirement that the final end result of jets should be unchanged if there's some soft emission or some collinear splitting, some almost basically one jet splits into two, one particle, for example, splits into two, but then the end result of the works is of the jets is the same. And the tracker, though, there's also not necessarily any connection being made between individual E and H particles, which just everything is lumped together and taken face value more or less, and then one can get some jets out, but then flow jets try to take that with better understanding, let's say, when instead of just looking at the calorimeter deposits and not making too many assumptions about how they may be interconnected, then the particle flow algorithm tries to reconstruct individual particles and makes a sort of global event description of what is most consistent. Not very well calibrated calorimeter. And then I also always find it useful to think about what are the ingredients that we need for a good general purpose detector. So on the one hand, we need, it's very useful to have a strong magnetic field, which then helps us to separate the particles by charge, and also enables, in conjunction with the tracker, to measure the transverse momentum, try to see what kind of curvature there is, and then the inner tracking that helps us to identify charged particles, but should in itself not contain too much material in order not to lead to multiple scattering, and also not to sort of initiate very early showers of particles that are only supposed to shower in the kilometers, for example. But there we can then measure all the charged particles at all these points and connect them, and from the curvature, if we then have the strong magnetic field, we can then determine the momentum. The calorimetry then is sort of destructive, and we have the particles showering, and then we can hope to usually by integrating the light that comes out of out of these showers, for example, in scintillating material, then we can also get an insight as to the incident energy of the particle that then started the shower. There one also usually has two more or less separate parameters, the electromagnetic and the hadronic one, because for the electromagnetic showers we only have the photons and electrons and positons in the pair production and bench carbon. And these showers are very regular and quite compact, but then these hadronic showers with nuclear interactions, they are much more messy, and those then also need longer absorption material to manage to do that. And then we have the muons, which are only weakly interacting, which then propagate through phospholipid parameters, and then we can have positional outer tracking, and if something is getting that far and can also do the inner tracker, then we can be pretty sure that it's a muon. And all of these individual pieces of the information are then combined by particle flow.
You can always add DD bar, and this way you can make a Mason pi plus and pi minus. Perfectly fine, there is no problem in creating this state from the quark content, from the 4 quark contents. And similarly, exactly the same quark content this 4260 has, and this particle. And there are now a lot of more states has been observed at Babar, Bell, CDF, D0, LHC, and 8 is the whole list of the states, and this is the slide I took from the talk of my over collaborator Alexander Cardone, and he actually gave a talk in 2021 at the NCP, and this is the whole slide of the talks, and you can see that these are the transitions like in the atomic physics. We know that atomic physics, when an electron comes from high state to low state, it emits a photon. It is exactly the transition like this one. I'm not saying it emits a photon, but Y4240 can behave to this thing, and this goes to this, so on and so forth, because everything seeks for stability, and we have to find a state that has to be relatively complex, and that is J by sign, which I'll give you second. And these are the J, P, C. P is the parity, and C is the charge conjugation. So now what's the parity? Parity is of the quark, let's say, is +1. Therefore, the parity of anti-quark is -1. It means if you have quark anti-quark, its parity is +1 into -1, therefore it is -1. But it also depends upon the orbital angular momentum. So the parity is +1, -1 into -1 to the power L. This -1 to the power L comes from the spherical harmonics. Because in the spherical harmonics, if you replace pi by pi, theta by pi minus theta, then you get this factor of -1 to the power L. And therefore, if they are L is equal to 0, they are negative parity, and if they are L is equal to 1, they are positive parity. The question arises, what are the exotic states? Exotic states are entirely different. In L is equal to 0, they have plus parity, in L is equal to 1, they have minus parity. So it's different from the ordinary cases. That is why these are known as the